So let's take a look at this problem. As a roller coaster car crosses the top of a 40-meter diameter loop-the-loop, its apparent weight is the same as its true weight. Now that's going to be a crucial thing we need to think about. What is the car's speed at the top? Well, to get started, to prepare, let's draw a more full-featured view than we usually do. Okay, we got to wrap our mind around what's happening here. It's a 40-meter diameter loop-the-loop, and if you've seen roller coasters like this, it's an inverted loop. So the car is going through the loop at some speed. It's upside down. Okay, so it's upside down, moving to the right. And let's think about the forces that act. There's a weight force which pushes downward. That's with us always. But now think about this. There's only one thing that's touching the car, and that's the track. And if you have a contact between two surfaces, I could have a friction force, or I could have a normal force. Well, let's assume there's no friction force because it's a roller coaster, and that tells us that it rolls smoothly, okay? But there will be a normal force, and the normal force will act here at the boundary between the two. It points perpendicular, and it points out of the surface. And so the normal force points straight downward. Okay, so I have a normal force which points down and a weight force which points down. I have two downward forces. Now both of them are pointing towards the center of the circle. So these are the forces that keep the car moving in its circular arc. Now let's continue our preparation. Okay, this is by way of preparation. Continue our preparation by looking at the motion and looking at the forces. We want to do this in some detail. The motion is just uniform circular motion. The car is moving through the loop. It's moving to the right as we've drawn it here. Okay, at a speed v. We don't know what the speed is. We're just going to call it v. We're asked for the speed. That's in fact what we're trying to solve for. And since it's moving in a circle, there's an acceleration directed towards the center of the circle. Okay, we know it's a circle because it's a loop, so it's a loop, so it's a circle. Now the circle has a diameter of 40 meters, and that means the radius of the circular motion is 20 meters. Notice, you're given the diameter in the problem statement, you need to use the radius for your solution. That's a standard thing you'll find in problems of this sort. Now we know the magnitude of the acceleration is just equal to v squared divided by r. That'll be an important point for us. Let's look at the forces. Well, there's two forces that act. There's a downward weight force, and there's a downward normal force. So the net force is just the sum of these two. They're pointing in the same direction. They're both pointing downward. And so the magnitude of the net force is just equal to N plus W. Those are the only two forces that act in the same direction. The magnitude is just the sum of the two. Well, the magnitude of the net force is equal to m times a. We know the acceleration because this is a uniform circular motion problem. And so we're ready to take the next step and solve. And a solution is going to use this fact right here. The magnitude of the net force is just equal to m times a. That's Newton's second law. Well, the magnitude of the net force is N plus W, and that's equal to m times v squared divided by r. But remember, up here, we said the normal force and the weight force are equal to each other because the apparent weight is the same as the true weight. So the magnitude of the normal force is equal to the magnitude of the weight force. So just rewrite it as 2 times W is equal to m times v squared over r. Well, the definition of the weight force is m times g. So 2 times m times g is equal to m times v squared divided by r. And notice what's happened. I have an m on this side of the equation. I have an m on that side of the equation. They cancel, which is good because we weren't given the weight. We weren't given the mass of the car in the problem. So this is a good assessment that we're on the right track. We weren't given m. We don't need to know m. It cancels. Our result is independent of the mass of the car. So what I get is this. I'm looking for v. I can rewrite this equation this way. V is equal to the square root of 2 times g times r. And so I can solve for this. G is 9.8 meters per second squared, so I get 2 times 9.8 meters per second squared. The radius is 20 meters. Check our units. I have meters squared, square root meters, second squared, square root seconds. So my units will be meters per second. My numbers give me 20 meters per second. So that's what I get for the speed of the coaster at the top of the loop. Now let's do some assessment. Let's assess this result. And I'll start here. First off, mass canceled. I wasn't given the mass, I didn't need the mass. And that's important because if the mass of the car made a difference to the speed, you'd have to send the roller coaster at different speeds depending upon the weight of the passengers. And that is not a recipe for success. So we expect that to cancel. It did cancel. Everything's good. Our units worked out. That's kind of a good check on our work. But finally, we want to do an assessment to see if this makes sense in terms of our experience of the world. Think about these upside down coasters. They move pretty fast, but they don't move at like highway speeds of cars. So we get 20 meters per second. 20 meters per second is about 45 miles per hour. So it's quick, it's a thrill ride, but it's not like scary fast. Thrilling, but not scary. And this matches with my experience of coasters. And so we'll say, ultimately, this matches with our experience of the world, and that's our best check on whether we've done our work correctly.